Good afternoon. My name is Eden Kim, and this talk is on real-world data center workloads and advanced storage architectures. It's a 60-minute slot. I've got 40 minutes of flexible material. Part of it is going to be looking at the testmyworkload.com website, and I may do a demo, or I've got slides that show it, but you can also go there, testmyworkload.com, and there are examples and things you can look at, okay? So, oh, by the way, I'm CEO of Calypso Systems, which is a SSD test and measurement company, and we specialize in test equipment and workload analysis. And I'm also the chair of the SNIA Solid-State Storage Technical Working Group, which has recently published a PTS spec, performance test specification for data center real world workloads. Okay. Do I dare go to full screen? Oh, I hate this view. Okay. So when we talk about real world workloads, it's kind of often been called the holy grail of compute and storage because what's inside your real world workload really dictates the performance of both your software and your storage. So real-world workloads are generated by user activity when you run applications or you run servers, and the workload that you look at is a capture of all of the I/O streams that go from point A to point B in the software stack. So that can be from the file system to the block I/O level, it can be block I/O level to storage, it can be two ends of a wire. So workloads are kind of universal in that everybody has an interest in what's in their workload because the content of that workload dictates how well your software optimizations or your architectures perform. As far as storage is concerned, there are many, many different architectures out there now. You have fabric storage, enterprise storage, virtual storage, you have direct attached, you have SAN, NAS, LUN, you have object, you have open, it goes on and on and on. But in each case, the storage architecture performance is going to depend on the real-world workload. Okay, why? Because what's in the real-world workload really affects how well the software manages the I/Os as the I/Os go down the software stack. So why are we interested in real-world workloads? Because these workloads affect how well the software works and how well your storage servers work and how well your web portals function, they're increasingly important for enabling emerging technologies. Things such as 5G video edge servers, artificial intelligence, so on and so forth, are very dependent on the I/O content. There's a lot of sophisticated optimizations that depend on taking the workload and optimizing the I/O streams, predicting what's going to happen, optimizing the I/O streams, coalescing them, deduping, compression, so on and so forth. So understanding what's in the real-world workload is key because this is very different from a synthetic workload that you might use in the lab. So how are they different? A lab workload is a fixed synthetic I/O stream which is applied to the storage to see how the storage performs outside the range of normal operation. It's a corner case test. You saturate the drive, you pound it with random 4K writes, or you see how much bandwidth it can handle. A real-world workload, on the other hand, is comprised of very, very many I/O streams that are constantly changing from moment to moment, and the queue depth changes. So instead of having a fixed and constant workload where you can predict I'm going to get 50,000 IOPS at steady state after 3 hours of test, your real-world workload is going to be changing every step of that capture or test and be applying a different combination of I/O streams and queue depths to your storage. So a storage may be very good at doing random 4K read-write and sequential 128K read-write, but may not do well at smaller block sizes or different types of accesses. And if your real-world workload has those different types of accesses, even though your drive may be advertised as 50,000 4K write IOPS and 500 megabytes per second, it may not have that performance when you run your real-world workload. Okay, so to put it in English, if I go buy a drive, drive A is 50,000 IOPS and 500 megabytes per second. Drive B is 25,000 IOPS and 250 megabytes per second. Okay, drive A is twice as good as drive B. But if the workload doesn't have random 4K read-write in it, or sequential 128K read-write, then what are we measuring? Oftentimes, data center workloads are comprised of many, many IO streams, and they aren't traditional block sizes. Typically, a SQL server is dominated by sequential half K writes and random 8K read-writes. So if my drive operates well to those IO streams, my 50,000 IOP, 500 megabyte per second drive may not do as well as the 25,000, 250 megabyte drive when used to the real world workload. Okay? So what you're seeing up here is a view of a data center real world workload. In the middle is what we call an IOStream chart, and on the bottom is the x-axis shows you time, and the y-axis shows you IOPS and queue depth. So as you can see, the blue dots, the IO rate and the IOPS go up and down over time, and the orange line is the queue depth of users that goes between, in this case, 6 and 306 queue depth. The colored bars that go on a profile from low to high towers are a mixture of IO streams, and each color represents an IO stream. So in this case, for this 24-hour SQL Server workload, which was captured on a retail web portal with 2,000 stores, the dominant, 9 IO streams are shown on the right-hand side. So you can see random 64K read was 18.5%, sequential half K write was 17%, random 8K read was 10%, so on and so forth. And we see random 4K writes down there at 4%. So in this case, had you bought a drive for its random 4K write performance, it would be only 4% of the workload you're looking at. In addition, those IO streams on the right are the average across the full 24 hours. So we add up all the IOs that occur, and then we divide, and we see that of the total number of IOs that occurred, 18.5% were random 64K reads that occurred somewhere over that 24-hour timeline. As you go across the IOStream map, those IOStream combinations are going to change. So if you look at that tall tower on the right-hand side, that orange tower, that's a 1 a.m. backup. And that particular IOStream is dominated by random and sequential 64K read-write. You're reading from drive 0 and writing to drive 1. If you look in the middle of the screen, you'll see some small sequential half K writes that relate to morning boot storm. And if you look at the tall tower on the right, you'll see a bunch of mixed IOs that have to do with the daily activity. So depending on where you are during the day, you're going to have a different combination of IO streams. Okay? So it's quiz time. How many of you are awake? All right. An IO stream is a specific randomly sequential access of a block size of a read or write IO. Okay, so random 4K write, that's one IO stream. If I have 50,000 random 4K writes in 24 hours, that's one IO stream. If I have 50,000 4K reads, 2 IO streams. If I have a 4.5K read, 3 IO streams, okay? So here's the question. Across 24 hours, how many distinct IO streams do you think occur? 100 or fewer? 500? Raise your hand when you think. 1,000? 2,000? Nobody's raising your hand. 25 million? Oh, okay. How about 5,000? Okay, so if you read on the bottom right, it says these 9 IO streams represent 71% of the total IOs, and there are 5,038 IO streams. Okay, so from midnight to midnight, 5,038 different IO streams occur. So as I said, the random 4K, 4.5K, 4.25K, 1K, 128 byte, it goes on and on and on. But a select few groups of IO streams dominate the workload. So when you see here again, you're seeing 18%, 70% are random 64K read and sequential half K write. So you can filter this IOStream map to show the IO streams of interest, which constitute some threshold of the IO streams. So in this case, we're saying, I just want to see all the IO streams that are 2.78% or more, or IO streams that constitute 71% of the IOs, and it will show those IO streams. So when you look at the colored bars across the top, they correspond to these 9 IO streams, okay? You can present more or less IO streams by occurrence, by IO stream threshold, by process ID, by event, by a bunch of different criteria. So for example, each IO stream is tagged with a process ID by the kernel. So it says, oh, this IO was generated by SQL Server. Oh, okay, I'm interested in that. How many IOs are SQL Server? So you can look at the process ID, tag all of the SQL Server IOs, and it will show those. So we'll do that in a minute. But I just wanted to show you here, the nature of this real-world workload are 2 things. You have a constantly changing combination of a whole bunch of IO streams that are not traditional block sizes, okay? That's number 1. And number 2, the queue depth is changing up and down. So those of you who do storage tests or performance know that my performance is going to depend on my queue depth. If I saturate with 1,024 jobs, I'm going to have lower performance, higher response time. The same way, I'm going to have different performance if I have a large block sequential workload or a small block fragmented, especially if I have a small block fragment in front of a sequential streaming read, okay? So these IO streams are dynamically changing from moment to moment, and that's how your storage and that's how your software needs to handle it in order to perform. The second thing is, these IO streams that are going from user space to storage and back go through different layers in the software stack. And at each layer of optimization, those IO streams change. Okay, so you can start in user space with a sequential 1 megabyte read, and that can be broken up into concurrent random 128K reads. And then it can be coalesced with some metadata. So by the time it gets to the storage, it's some weird size like 398 or 396K or 64.5K or a bunch of different things. And then when we send the IOs back up to user space, it's going to metamorphize again, and I'll get my, what do I start with? 1 meg sequential, okay? So depending on where you are in the software stack, you're going to have a different type of real-world workload. So why is that important? Well, if I'm testing storage, I want to be as close to the storage layer as possible. Or if I'm doing dedupe or compression, I want to be at that level where I'm compressing the IOs. Or if I'm doing storage tiering, I want to be able to direct the IOs according to my algorithms so that my small block fragmented workload goes to my hot cache, and my large block streaming goes to the spinning Rust, and my mixed IOs go to my NVMe SSDs. Okay? By the way, you can ask questions because I don't really have that much material. Okay, so let's look at a couple of different real-world workloads. The one on the right there is the one on the right is the Datacenter Retail Web Portal 2000 store outlet. And I get to use this fancy thing. It doesn't show up. Okay, so what you can see here is the IOs go up and down, and the IO streams have that profile where there's a peak and a valley and then a growing mountain pyramid. The IOStream Map in the middle is a GPS nav portal, which is a 97% write workload. The first one was a 65% write workload. Okay, so the first thing you can look at is the read-write mix. The second thing is the middle drive is drive C. So it's dominated by those blue IOs, which are shown as the red IO stream, and those end up, and they happen to be sequential 128-byte reads. Okay, so nobody tests sequential 128-byte reads. Why? Because at the storage level, it's not going to be a 128K byte read. Those 128-byte reads are going to cache, okay? And then it might be coalesced into a 4K block size or page size and then sent to storage. On the right, that's that same GPS nav portal, but now we're looking at the block IO level for drive 0. So even though in the middle, in user space, we had 70% of the IOs being sequential 128-byte reads, when you get down to the block IO level, you're seeing it's dominated by a very constant mix of traditional block size IOs. So you can see that red band, green band, blue band, and orange band is kind of consistent across. So that same mix of basic IOs are occurring all the time. What's also interesting, you'll see there's 4 spikes. Those 4 spikes happen to be sequential half K writes. Okay, so why are they there? Well, if we were to look at those IOs, we could see what the process IDs are, and it might give you an indication of what's going on. Maybe it's generated by the system, maybe it's a SQL Server IO, it depends, okay? So you can see here 3 different real-world workloads. They look very different when you look at them from a top-down view over 24 hours. And then each one looks differently depending on what time you look at it, right? If I do 1 a.m. or 8 a.m. or 6 p.m., I'm going to have a very different workload. So when you look at a real-world workload, it's really important to know, is this real-world workload taken from a storage server system that's similar to the one I'm going to use? Okay. Second, is it running the same sort of applications? Third, does it have the same demand intensity running? Okay. And then fourth, what kind of storage is it going to? Because the nature of the workload you see is going to be influenced by the storage to which it's being written, right? So in a real-world workload, the application space is essentially throttling the IOs going to storage. If you look at the IO rate of any of these, the IOPS is very low. It's like 100, 500, 1,000. Well, why should I buy a 50,000 IOP drive if my IO rate is only 100? It's because the application is driven by the users, and there aren't that many users, so the IO rate is lower. If you were to take that workload and apply it in an unlimited fashion to storage, you'll get a much higher number. So what you do is you take your workload, you make a test script of those IO traffic profiles, and then you run it against storage in an unlimited fashion in the lab, and I'll find out that my NVMe SSD won't get 100 IOPS, it'll have 100,000 IOPS. Okay, so you can compare your NVMe SSD to a persistent memory Optane drive to a spinning disk hard drive with the same workload, and you will get the maximum performance that each storage can get given that workload. But in the real world, you never actually have a case where your storage is at 100% utilization. Otherwise, you haven't designed your system correctly, right? I mean, yes?
So what is significant of drive 0, drive C? Or just label you're using here?
So drive C is the system. Drive 0 is block I/O. Okay. So file system is C, and then it goes to drive 0, which is where block I/Os occur. In the first case, drive 0, drive 1, there's 2 drives, and I'm reading from one drive, writing to the other drive, back and forth, backing up, doing X copy, disk copy, those type of things.
The storage configuration of these drives are just different? I mean, you just happen to take these as examples?
Yeah, these are just examples. You can apply any workload to any storage, right? So I can pick the workload coming from a given server at a given point in the stack. So I want to do it at the block I/O level, and then I can go ahead and apply that to direct attached storage in my lab, plug an SSD into my server, or I can hook up to a LUN or an array or SAN or whatever I want. Okay.
Where is that captured? Is that captured at the application server layer, or is captured?
So you can capture a variety of different levels, okay? But the most common levels are to capture at the file system level and at the block I/O level. So in this picture here, you can see the circle that says I/O profiler. That indicates both the capture tool as well as the test point. So if I capture in the file system, I'm going to be getting a lot of I/O traffic that's going both to storage and to cache. If I get at the block I/O level, I'll be above the HBA card, and I'll be seeing traditional size blocks going to storage. Okay? Zooming ahead. Okay, so if you go to testmyworkload.com, you can download an IO capture applet that looks like that little circle in the bottom. And then when you load it, you open up the applet and it says IO profiler. You can pick a time, a resolution, and the file system or block level to do the capture, and then it'll run. So if you go to Test My Workload right now, you could, how do I do this? Okay, so if I go down here, if I go to testmyworkload.com, down here there's an applet. I'm on a Mac. I could click this and download my millionth copy, but I already have it. Okay, so there's my IO capture applet. I open that up, and I'll see that little console. There's my console. I put my glasses on, and I can say, okay, run 5 minutes, do temporal resolution of 1 second, resolution of 1, and block, and start. So now, the hardest part is putting in your password. Okay, so this thing is running now. It's doing a capture. There's really nothing going on my laptop, so I'm going to go over here, And I'm going to open YouTube. And we're going to just randomly pick something. But turn the sound off. Okay, so this is running in the background. Okay, so we're doing an I/O capture. And what's an I/O capture do? It goes in the layer of the stack, in this case at the block I/O level, and it watches all the I/O streams that are going from point A to point B. And it tabulates statistics on those I/Os. So if I see 50,000 random 4K writes, I make a table entry. I saw 50,000 random 4K writes. Okay, random 4K write 50,000. I'm not actually capturing 50,000 4K or a million bytes, right? I'm only doing a table entry. So instead of capturing the actual I/O data, which is done in an I/O trace, you're capturing statistics on the I/Os that are going by, and you're binning them by step size. Okay, so if I did a continuous I/O trace, I might get 50 petabytes for a 1 hour capture, and all the data is in there, and I've taken the data from the server, and the IT administrator is pissed because I'm not supposed to be on there, I'm not supposed to take his data. But if you use an I/O capture tool, I'm just sitting there and I'm watching the I/Os go by. There's a half K write, there's a sequential 128K, blah, blah, blah. I've got a table of randomly sequential, block size, read-or-write mixes, and the metrics associated with it. Well, this one had an average response time of this one had an LBA address of this, so on and so forth. So these tables of statistics are much smaller than taking the actual data. Okay, they don't have overhead, so the CPU usage is less than 1%. And when I'm done, I have a portable file that I can actually email and use instead of figuring out how am I going to get 50 petabytes from the capture location to my server and look at it. Okay, so the benefit of an I/O capture is you don't take any actual data or any personal data. You can set the temporal resolution, the time steps, so that I can take a lot of data over a broad period of time without having a large file size. So if I want to do a 24-hour capture, I can do it in 1 minute segments, 1 second segments, 5 minute segments, whatever. And I'll be able to see the IOStream traffic, like that little profile we saw earlier. That's at 5 minute step resolution. So it averages all the IOs that occur over 5 minutes and shows them on the map. Equally, I could do a smaller grain resolution and go to 1 microsecond and show 1 million steps per second. So you can vary the resolution you want depending on what kind of view you want. So if I want to see IO sequentiality, IO bursts, I want to see trims, I want to see latencies, I can go down very, very fine resolution. Or if I want to know generally what kind of IO streams is my workload generating over a week or a day or a month, I can set it to a 5 minute or a 10 minute or a 1 hour resolution and just get a very coarse grained picture of what's going on. In either case, I can download the file easily and look at it, and the IO capture tools will allow you to visualize and filter those IO streams to see what you want to see. It won't just be this mountain of incomprehensible data. You'll actually be able to see what you want. So in this case, have I talked for 5 minutes? Oh, I didn't press start. No, wait, that's not the real one. We got to go to the real one. Okay, it's still running. But if I go to testmyworkload.com, you can go here and say, I've signed on, I have an account. I can go, waiting for bandwidth. All right, what we're going to do is we're going to do this. Okay, so this example, I'm in the demo section. This example number 5 is that 24-hour retail web portal, which is the same thing we saw on the first slide. So here's drive 0, here's drive 1. It's a 1-day capture. There's 720 steps. Each step is 5 minutes. You multiply that out, that's 1,440 minutes, which is a day. Okay, there's drive 0 and drive 1. And so when I go to drive 0 and I open this, I'm going to get an IOStream map, which is going to show me on the x-axis time, and on the y-axis, the I/O count and other metrics. And you'll see the colored bars going across that should be similar to that picture. So here, what you have is, here's my IOStream map. I'm going to get rid of these workloads that I've selected. So here's that 2 a.m. spike. Here's the morning boot storm. And here's the peak. And when I overrun each of these, I can see in the tooltip, at 647, I had random 64K reads, 39,945, of which 39,863 were SQL Server, and 79 were system, and 3 were W3 WP. I can go over here and look at this guy, which is my backup, and it's random 8K reads, 1,000, and it's random 64K reads, 640. If I click this, it will give me a workload box that says that 83% of the items here were sequential 64K reads, okay? When I hit the Processes tab, this shows me the process IDs. So when I look over here, 79% of all the IOs were SQL Server, 13% were system. So I can clear these and say, let's just show me SQL Server IOs and apply it, and it rebuilds the IOStream map. And now when I tool over here, every IO says SQL Server, okay? Or to show you more graphically, we can say, let's just take Xcopy and let's apply that. So now everything disappears because Xcopy only occurred here. And if I highlight this, oops, I missed. If I highlight this, it says Xcopy. It's random 4K reads and sequential 4K reads, 6625. And there were 2 streams, which were 92% of the IOs. So you can filter the workload that you captured by time, by event, by IO streams, by process IDs. And you can also do it by the number of IO streams that you want to see. So if I select all these and go back to the beginning, if I see this IO stream threshold, it says 3%. So here on this workload, I've got 6 IO streams. The smallest one occurred 3.5% of the time. The next 2 are grayed out, 2.9, 2.7%, and the third one is 1.9%. So if I drop the threshold from 3 to 2%, I'm going to pick up 2 more IO streams in the 2% range. So here it says right now at 3%, right here, I have 6 IO streams, which is 64% of my workload. And those 6 IO streams are shown on the map. If I change this to 2%, it redraws the map, and now I pick up those 2, and it's 8 IO streams for 70%. So now if I get rid of the descriptions, I can see in the IOStream map, I've picked up 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you can do a lot of things that way. You can also look, instead of at the frequency by IOPS, I can change it to amount transferred and look at the bandwidth in megabytes per second. And I can also look at drive 1. I can do a bunch of things. So you can go on to testmyworkload.com. You can download an applet for Windows, Linux, or Mac. You can do your own capture of any activity you want and upload it and look at it for free. Okay? Yes?
Do you capture quality of service information?
Yes. So we capture all kinds of response times. You get 5 nines response time. You get max response
Set your
times.
resolution down really low.
It automatically takes a whole host of IO streams, but if you buy the commercial product, you can pick and choose what you want. But the default mechanism gives you average response time, max, and 5 nines quality service. You can also look at compression, dedupe, trims, a variety of other metrics. Okay? So we've got that guy. Going back to here, so this is the IOStream map that you saw. And when you look on the right-hand side, that's the description of the workload, the cumulative workload. On the left-hand side, those are the process IDs. There's 36 process IDs tagged by the kernel. Now, it may say that 8 million IOs were tagged as SQL Server. That doesn't mean that all the SQL Server IOs are 8 million, because a lot of the application IOs get buried in the system because it gets loaded, and the system is in memory and it runs. So you can see IOs that are specifically generated by an application, but there may be other IOs associated with it that are masked by system. Okay? Along the bottom, you can see the different points in the day. So we've got 1 a.m. backup, we got early morning low utilization, you've got morning boot storm, you've got daily work activity and closing, and you can see the red line is the maximum queue depth, or users. So you can see that mid-morning it's a flat line in single users, and then during the day it goes up to almost 300 users. Okay? So the neat thing about this is you can capture this workload and then you can parse it to get those things that you're interested in. So I might be only interested in the SQL Server stuff. Okay, great. So we just click SQL Server, unclick everything else, click it, the whole thing is just SQL Server. Now what? You can make a test script from that, and what it'll do is it'll automatically make a test script which recreates the sequence of those changing combinations of IO streams and queue depths into a test script. Then you can apply this test script to any storage you have. So I can capture this workload on my retail web portal, I can make a test out of it, and then I can test my LUN or my network attached storage or my direct attached SSDs in my lab using this actual workload. And then I can compare that to synthetic benchmarks. So again, in our earlier example, I've got 100,000 4K random write SSD, but if I use this workload, I might get a different number, and it may be better, the same, or worse than the 50,000 random 4K write drive. Okay? These next few slides just show you different metrics that you can look at. So I'm just going to kind of skip through this. These are the various metrics you can look at: dedupe, trims, IO sequentiality, compression. And then what you can do is you can also do a real-time plot. This real-time plot takes that real-world workload, and when you test your storage, you can replay the IOs that occur in your storage over time. So we took that real-world workload and we ran it on this Optane persistent memory drive, and the blue line is the IOPS, the orange line is 5 nines quality of service, and the green line is average response time. So we ran this across time, and the IOs and the IOPS range between 500,000 and 3 million IOPS, okay? And the response times varied from 0.3 milliseconds to 0.016 milliseconds. So 16 microseconds to 300 microseconds, all right? So what's interesting about this is you can take that real-world workload, run it on persistent memory, run it on NVMe SSD, run it on hard disk drive, and you can get this map and compare how each of those perform. Once you find out how the storage performs to the real-world workload, you can then optimize your software or your storage based on what's in that workload, okay? So let's do that. Here are 3 NVMe SSDs, U.2s. U.2H for happy, U.2M for Mary, and U.2S for smiley. Those letters do not relate to big SSD companies that might start with the same initial. U.H is faster, happy is faster than Mary and smiley, 4 times and 5 times faster. 200,000 IOPS averaged over the 24 hours to 72,000. So 200 to 75 and 200 to 58. Okay, so it's 4 times, 5 times faster on average. Okay, that's great. That's using those 9 IO streams we saw. Remember, it was 18% random, 64K read. It was like 20%, 24% sequential half K writes, so on and so forth, and random 4K writes were 4%, I think. Those are changing with every step, and we got an average of 200,000, 75,000, and 58,000, okay? If we look at those drives now, just looking at random 4K read-write and sequential half K write, in that workload, 24% of the workload was sequential half K write. 4% was random 4K read, and 5.7% was random 4K write. So the orange drive, the smiley drive, is better at 4K read-write. So if you're going to buy a drive, yeah, I got better random 4K read-write performance. Oh, buy that one. Okay, but the workload is 24% sequential half K write, and only 10% random 4K read-write. So the happy drive is 258,000 to 160, almost twice as fast, 24% of the time. Okay, the orange drive is 32 to 27, maybe what, 15, 20% faster for 10% of the time. Which one's going to be better? Okay, so this goes on for all the IO streams you have. And it also goes on for the response times and the sequence of the IOs, because some drives do better when you have a transition from a small block fragmented random IO to a large block sequential read, okay? So depending on that, depending on the demand intensity, how many queue depth you have, your drive is going to perform differently. But in this case, we just took the workload that we saw on that retail web portal, we applied it, and hey, I average it out, happy is happy. I'm 200,000, okay? Smiley's not, actually he's sad, he's only 28. But on the box, Sad as Smiley because he's got better 4K read-write performance. So beware, okay? Benchmarks are there, but buyer beware. Mm-hmm.
One of the challenges that I think is that it's a function of which set of chips you're accessing the SSDs. And that would be a function of when you went to read or write, which location you actually said needed to be read or written. And
Sure.
therefore you would get different types of performance based on the different types of drives. And that would not still represent what your real workload would be, because you have already changed the locations
No, no.
of your reads and writes.
The inherent performance of your device is going to be there depending on what kind of I/O is applied. But we're applying the same I/Os to two different storage devices. Okay, so you're getting the same sequence. 4K, 8K, 4K is my workload.
I get that, but 4K, which is hitting the wrong set of chips all the time.
Well, it's a black box, right? Whatever it is, it's transparent to us. We're applying the I/Os to that storage. And it's up to that storage how much it wants to be over-provisioned. It's up to that storage what kind of firmware it uses. It's up to that storage how good it's going to be at 4K writes. Okay, but I don't care because I'm applying 4K, 8K, 4K. How fast were those three I/Os? 50,000. How fast were they on this guy? 100,000. So that 100,000 guy is faster. Why? We can go into it. Maybe he's over-provisioned. Maybe he's got more channels. Maybe this, that, and the other, whatever. But it doesn't matter because I'm just getting the drive. And drive A and B are being subjected to the same workload. And the workload comes from my actual usage. And it's comprised of a whole bunch of different things that actually occur when I use my system. Okay, so you have to distinguish between what's going inside the workload, what's going on inside the SSD, and what's going on external to the SSD as you apply the workload. You're absolutely right that internally it's going to depend. But, plugging a different, I have two SSDs. I'm giving them the same workload.
And what was the state of these SSDs?
Well, it can be,
When they started out.
it can be FOB, it can be it can be steady state, it can be whatever you want. The point is that when you actually are running in the wild, nothing is purged, nothing is FOB, right? So you can choose what write history you wish to start at when you do your test. But if you do the same setup to two different drives, you can compare them. They might both be 1 week old, they might both be a year old. One might be brand new, one might be a year old. You can compare those if you like as well. Okay, all these things occur and they are all absolutely true. But the point here is you're going up the stack and you're looking at storage as interchangeable logical units that I'm applying a workload that's generated in a given environment to those logical storage units.
This is a lot like what Rogoff and Trell did 3 years ago. And their first approach to it was, it depends. But then the more interesting question that was not resolved by their discussion about it was, why do they behave like that? Now, but I have a question about when you were generating traffic load, you had simply retained all the metadata about how many packets, what sizes they were in, and the payloads were completely arbitrary when you regenerated it.
Right.
Is that true?
Yeah.
Okay.
It's a standard I/O generator. You could use FIO, you could use iometer if you want, whatever.
How did you control the number of threads that were generating this I/O?
So on the test side or on the capture side? On the capture side, you just see what you see, and the threads aren't really noticed. They're just showed up as queue depth. So I have a queue depth that goes in this example from 3 to 300. So every step, it might be a queue depth of 3, 55, 100, 15. So for every test step, I go 5, 55, 100, 13 is where we set it. So we set queue depth native means do the same queue depth that we saw in the original capture. You can also scale it and say that, well, I know that that server is underutilized. I want to really test my storage. If I keep the queue depth too low, I'll never know what my performance is. So let's scale everything up by a factor of 10. So that 15 becomes 150, that 100 becomes 1,000, and so on and so forth. So you can scale your workload according to how much demand intensity you think is relevant for your test purpose. Yes?
So you're saying that the scripts you generate with the pattern are going to run using different I/O generators, just not one that comes with the software?
Oh, yeah. If you buy the commercial tool, which I'm not allowed to talk about, it has its own software generator, and it's actually the SNIA PTS test software made by a company that's on the front of this presentation. But you can look at that workload in terms of its steps and its I/O pattern and create that in any software generator like VDBench, Iometer, FIO, because step one will be run 50% random 4K write and 50% random 4K read at a queue depth of 10. Okay. The next step, do 8K read write at a queue depth of 20. Now, if the software doesn't allow you to change the queue depth from each test step, you might have to concatenate many different tests together. More sophisticated test software allows you to change the settings for every I/O step, and you can have hyper-threading, multiple I/Os, all kinds of different things going on.
Does the sophisticated software let you run over NAS protocols?
Yes. So back on that first picture you showed, we had all the architecture. You can test remotely to anything you can see. And so what you do is you put the back-end test software generator on the target server, and you communicate to it and say, hey, run these I/Os to your storage. And then when you get the data packets back of the results, those get sent to the control server that puts it in the database and then creates those the replay test and the data results. She just gave me a sign back there that says there's 5 million people in the audience, and this is the biggest crowd ever. Nobody knows better than I do. So you don't want to look at this fake data. You want to look at the real data. I'm sorry, joke. Yes, question?
When you're done, I would like to know what's the takeaway from your presentation?
The takeaway of the presentation is you can test using synthetic workloads or real-world workloads. They're all good. But to know how your storage is actually going to perform, you better use the real-world workload. Why? Because performance depends on all those different I/O streams. And when you can see what's in there, then you can determine which storage is going to be better. The second thing is, if you're optimizing the stack, you can see what the I/Os are, and instead of making some cool model, you can actually look at actual data and say that I am getting a bunch of fragmented data. I need to coalesce to make 4K page sizes. But if I'm getting large block sequential stuff, coalescing doesn't make any sense. Or if I'm saying I'm going to compress, if I have totally random data, there's no point in doing compression. So it validates those software optimizations. The third thing is, it allows you to validate and qualify storage by using the actual workload that the storage is going to be when it goes in there. So you take a data center workload and you use it to qualify the data center storage servers to see how the server is going to run to the data center workload, not how the random 4K read-write and sequential 128K read-write are. Okay. Okay, so for persistent memory, here's a chart that's going to give you a headache. On the left-hand side, traditional apps go through PCI bus, SSD stuff. That's what we do. Block I/O level, run the I/Os. In the middle, PM driver, you can take a block I/O workload. The PM driver will turn it into byte addressable, load and store, and allow you to test persistent memory. You don't have to do anything. So I'm going to just take my block I/O workload. The persistent memory driver magically turns it into stuff that persistent memory can do. I don't have to hear about it. I just get a number back that's faster than traditional SSD. Or if you go to the right-hand side, use PM-aware applications. Now I'm using native load store, mem copies. I can get really good performance, but I got to be aware of what workload is going to my storage. And in the case of persistent memory, there is a caching that goes on where we send all the writes to DRAM, and we send the read workloads to persistent memory. Why? Because persistent memory is a lot slower than DRAM for writes. Okay? So if you knew what the rewrite workload composition was, you could direct all the write IOs go to DRAM, all the read IOs go to persistent memory, and things would be cool. If you get it the other way around, your PM's gonna be really slow. So when you look at this, here's that IOStream map, and you can see the line going up and down. That's your performance. Each column, the red are reads, the green are writes. So you can see that for any given period of the map, you can see if it's 100% read, or if it's the bottom square, it's 100% write, or it's anywhere in between 80-20, 60-40, so on and so forth. So as we said, we could take that 1 a.m. workload, and we can see that it's 50-50 read-write. You can look at the morning boot storm, you can see it's 100% write. So you can look at your workload as it occurred when you ran your application and understand what the nature is of the workload at a given point in the day, and know if that should go to persistent memory, should go to DRAM, or should go to spinning disk, or wherever. So it really helps for storage tiering and advanced and sophisticated optimizations for managing your storage IOs. This is a very simple chart looking at, this is looking at endurance. So we can look at each IO stream, and we can calculate how many total media writes there are and calculate the 5-year, 1-year total petabytes written. So why is this important? Because if you're going to put DRAM and persistent memory together in a server, you want the persistent memory to last as long as the DRAM. I don't want it to burn up and be dead in a year because it's out there. I'm not going to be able to replace it. So you can look at the IO streams, and the IO streams, depending on the nature of the IO stream, will have a different endurance rating. So you can confirm with fine granularity how much writes, how many writes you can expect to get with persistent memory. Okay? I have 2 minutes left for all the good questions. So go to testmyworkload.com, download the tool, and do a capture. If you do a capture, yes?
Does the capture tool affect the performance of the real world workload you're recording?
So when you do a capture, it has about a 1 to 2% overhead on the CPU usage on a multi-core system. So it's pretty nominal. Yes?
So you talk about synthetic workloads not really being representative of real world performance. The performance test spec in SSSI, is that an effort to try and
Right, so there's two test specs. There's two test specs. The synthetic PTS spec goes to your traditional benchmark corner case tests, and the real world workload gives you a methodology to capture a workload and test it using the real world workload and compare the two. So drive A is twice as good as drive B, is twice as good as drive C using synthetic benchmarks. A, B, and C are all the same using the real world workload. So therefore, you can buy either one. Or endurance for A is twice as good as B, is twice as good as C using JEDEC 219A, but using the real world workload, it doesn't matter because they have so many reads, they last forever, so don't spend your money on drive writes, spend your money on sequential half-K write performance. Yes?
Does the tool just target one drive at a time?
No, it targets all the logical storage seen by the OS. And with, like you saw those tabs, you saw drive 0, drive 1. I mean, if you had a cluster, you could have drive A to drive AAA or XXX, right? Okay? My time is up. Thank you very much.